So module 7, it's a big module, lots of content. The focus of the content is very different to module 6, slightly different to 5. Whereas module 5 and 6 was a lot of conceptual understanding, a lot of calculation-based stuff. We shift off that in module 7 and we enter this very content-heavy term where we need to get a big understanding of all these different molecules and how they work, but also understand what those structures of these molecules would mean in terms of properties, how we can react them together, how we form them, and how we can use them in everyday life. So that's the idea. The way that module 7 flows, we start with naming. So we figure out how to name all of the molecules. From the naming, we need to figure out what the structure of all these molecules are. And the structure tells us about their properties, which can refer to how they react. So their reaction pathways, their formation, how we can make them. So that kind of relates to the reaction pathways. And lastly, their everyday applications. So this is pretty much the structure you're going to follow for the whole module. You'll learn about a particular type of molecule or functional group, as we'll call it. You'll learn how to name it. You'll learn what its structure is and how its structure causes its properties, which allow for reactions, for it to be formed, and for everyday applications of it. Today, we're just going to focus on this part. So content session 1 is just going to be naming and figuring out structure of all the molecules. With each session, content session 2 and 3 will shift down towards more focus on properties, or 2, 3, and 4 will be more on properties, reaction pathways, and formation. And content sessions 5 and 6 kind of lumps everything together. So we're building out our world of organic chemistry today. It's going to feel like a lot of new concepts we're building horizontally. And as the term goes on, we'll take 6 weeks to finish module 7. We'll build vertically upwards on each of our foundations. So think of it as today, we're world building. You're going to feel very inundated with information. Content sessions 2 to 5, we're building up on each of these foundations, our understanding of each individual molecule. Before we begin, are there any questions about how things will work this term or how module 7 is? Okay, great. So we'll start with nomenclature. If at any point you have questions, feel lost, stop me, ask your question, disperse the misunderstanding, and then we can all learn quicker together. Because the chances are, if you've got a question and you don't understand, someone else has the same question. Okay, nomenclature. How do we systematically name organic chemical compounds? The notes are organized by dot point, so we'll be following pretty much the same order as the syllabus. Organic nomenclature, we have to name chemicals up to a carbon chain of 8. And we should know what methyl and ethyl groups are. So these are alkyl groups. And we need to know all of these different, what we call functional groups: alkanes, alkenes, alkynes, alcohols, aldehydes, ketones, carboxylic acids, amines, amides, halogenated organic compounds, and esters. So we're going to do all of this today. It's going to be fast. There's going to be a lot of questions, so stay active throughout the session. We're going to use the chat line to type your answers in. It's totally okay if you get things wrong. In fact, it's probably better you get things wrong here than at school. So get things wrong, embarrass yourself. No one really cares. Everyone will leave here today, and no one will remember who got what wrong. So just get things wrong. What is organic chemistry is the first question. It is the study of carbon-containing compounds. So anything that has carbon in it would be an organic compound. And we're looking at the structure, properties, composition, reactions, and preparation of these substances. Most organic compounds will have carbon as well as hydrogen, and you can have an array of different nonmetals, so nitrogen, oxygen, halogens, and many others. The first thing I want you all to understand is how carbon can bond to itself, because this is what makes up what we call the parent chain or the main chain of carbon in any organic compound. So carbon can form 3 types of bonds: a single bond, a double bond, and a triple bond. And my first question is, how many electrons exists in a single one of these bonds? Hold up your fingers. How many electrons in one bond? How many electrons? 1, 2, 3, 4, 5, 6. 2. Gibran says 2. Correct. It is 2. We have 2 shared electrons in a covalent bond. And by definition, a covalent bond is where we have those shared electrons, where one of those electrons comes from one of the carbons and the other one comes from the other. So I'm going to stretch your minds all the way back to module 1 in year 11, where we drew electron dot diagrams. Does anyone remember those? Electron dot diagrams, Lewis dot diagrams. Between each of these carbons, or actually around each carbon individually first, how many valence electrons exist around one carbon? How many valence electrons? Hold up your fingers again. How many valence electrons? We've got a 6, we've got a 4, we've got a 6, we've got a 4, we've got some uncertainty. 4. Darren, what do you reckon? 4. Okay. So the confusion between 6 and 4, around each carbon, or if every carbon atom has a total of 6 electrons, but the valence shell will only contain 4. Because if you remember back from year 11, there was the inner shell of carbon, which contains 2, and then another shell, which will contain 4, and has a capacity to go to a maximum of 8. So the 2, 8, 8, 2, all the way back. This is now coming back into use. And the octet rule we learnt. Does anyone remember the octet rule? What does the octet rule state? Oct. We must have 8 electrons around every non-metal in order to be stable. So we must have 8 electrons around carbon in order for it to be stable. And that's why we form all of these covalent bonds, because it allows for these nonmetals to gain 8 electrons around each of them. So with each carbon here, each one starts with 4 electrons in its valence shell. And the question is, how do we then get to 8 electrons around each one in order to be stable? Well, the first bond comes about from the carbons forming a covalent bond between them. So this covalent bond in the middle is represented by a line. This is the same thing. This is synonymous. 2 shared electrons is the same as this single line in the bond. What else can bond on covalently to these single electrons coming off all the carbons? Type in chat. What do you reckon? What else could? Hydrogens, perfect. Anything else? Apart from hydrogen? Chloride, sure. Basically, any non-metal can bond onto these single electrons that are existing at the moment on their own. This would not be how carbon exists normally. Carbon has to have things covalently bonded to it in order to reach stability. So for example, a hydrogen with its single electron in its valence shell would be able to form a covalent bond with each of these as such. And this is what we actually see in terms of the electrons when we show, for example, all of these lines between C's, H's in our organic structure. And this molecule here is called ethane. We'll learn how to name it in a second. Does that make sense for everyone? Each of these bonds consists of 2 electrons and they're shared between 2 different nonmetals. Okay, any questions on that first of all? Great. We can then start to look at what all these different drawings of organic molecules actually look like. There's 3 different ways we can draw organic molecules. We have structural, condensed, and skeletal formula. We'll start with structural. I'll just clear these dot diagrams up here to give us a bit more space. So Structural diagrams are where we show all of the bonds and atoms. So every single bond is shown between every single atom, and it's the biggest thing. This is your default drawing. If you ever get asked to draw a organic molecule and you don't get told to use structural, condensed, or skeletal, you draw it in structural. That's the rule of thumb. So this is the one you'll be using the most. It allows you to see the most detail. My least favorite is condensed structural formula, so the one underneath. Sometimes you can draw this one without even showing any bonds, but the important features of this formula are you are allowed to condense any multiples of elements. So if you have multiple hydrogens, you can condense them into CH2 instead of showing them as a CH2 like this. So this is the same thing, but it's just been condensed. Same thing as a CH3. This can be condensed down. CH3 condensed into CH3. Finally, we have this form, which we call skeletal formula. So skeletal formula, as it sounds, it looks rather skeletal. It's just these straight lines. We don't have any hydrogens or carbons shown in lettering, but we show everything that is not a hydrogen and everything that is not a carbon. So here in this particular one, chlorines are being shown. And the question is, how do we see where the carbons are? How do we see where the carbons are? Does anyone know? Anyone have a guess? Just unmute.
Is it each point?
Each point. So would this count as a point?
Oh, it's more like each like branch kind of, like the line.
Yeah. So specifically, that's the right idea. It's each point, but it's every single corner. So corners, these are corners, 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 all intersections of these lines. Corners, intersections. So these are the intersections. And open ends of lines. Open ends. So this would be an open end. This would be an open end. And so all of these individually will be carbons. So then we have a total of 10 carbons in this structure. To be clear, when we have some other atom being shown on the end of a line, there is no carbon in this place. There is no carbon here. So none of these Cl lines have a carbon at the end. This is just a chlorine. Okay, so those are the drawings. Any questions on these? Okay, cool. Just adding some more terminology before we move into anything else. Substituent, side chain, and functional group. So you might have heard these terms thrown around if you started this already. If you haven't, that's fine. Substituent and functional group are quite closely related. Side chain is its own unique thing that you should not refer to as a functional group or a substituent. So what are these? Let's bring back our molecule from before, ethane. So this here is ethane. When you replace a hydrogen on a carbon chain with any atom, any group of atoms, we refer to that group of atoms as a substituent. So if we removed a hydrogen here and we replaced it with a chlorine, for example, this has replaced a hydrogen, and structurally, from a structural point of view, this is a substituent. But at the same time, this substituent or chlorine group provides this molecule with different properties and different properties, different ways to react. And so at the same time, it's also a functional group. So it's kind of both at the same time. But for the most part, when we talk about these in organic chem, for HSE purposes, we generally refer to most of these things as functional groups, just because of how they provide the different properties. And that's usually how we're talking about these things. So functional group. All of these things listed up here, except for alkyl, these are all what we call functional groups, where Fx is functional. Functional groups. Okay. Side chain is slightly different. So a side chain is where we have carbons coming off the main chain. So if I was to extend out my example here, let's replace this back with a hydrogen. And we have a carbon coming off of here. This carbon here is what we call a side chain. Side chain. So side chains are any carbon chain coming off of the main parent chain. And when I say parent chain refers to the longest carbon chain is the parent or main chain. Parent or main chain. Okay. Any questions on those three terms? All right. Two more, then we'll be on to the main stuff. Homologous series. So you might have heard of homologous series. Homologous series are compounds with the same substituents or same functional groups, and they have consecutive members in this homologous series, which each differ by CH2. And this on the right is the alcohol homologous series. So what I mean by this, each of these molecules all have the same functional group. All have the same functional group. But if you look at how they each differ, each one has the addition of a CH2 group to it. So you're kind of just chucking in a CH2 into the middle of the chain somewhere, and it extends one carbon along at a time. So it grows in length from 2 carbons to 3 carbons to 4 carbons, and this homologous series extends beyond 4, all the way to as many carbons as you want, as long as the functional group is the same and it's in the same place. So what I mean by same place, if you had, let's do this, and the OH comes off the second carbon instead of coming off the first, this would be part of a different homologous series. This would be a different homologous series because the OH is not on the same place as the others. We'll talk more on homologous series in the second session, once the properties become important. And finally, locants. So locants are basically just numbers that describe the position of the functional groups or substituents. Positions of functional groups. So looking at butanol, and this is what we call an alcohol. You don't know it yet, but we will learn about it soon. Butanol, you see that the OH group is on a particular carbon, and it's different, and it could be placed on any of the other carbons. So when we actually go and name all of our molecules, we need to specify where each individual part is located on the chain. And for this particular molecule, we have the OH coming off of the first carbon on the chain. And when we number carbons, we always start from one side and we number across, going 1, 2, 3, 4, 2, 3, 4, in order to make our numbers as small as possible for whatever function group we're naming. So this here would actually be called butan 1-ol, if we were being specific. And this 1 is what we refer to as a locant, telling us where our hydroxyl is located on the chain. Okay, so that's the foundational stuff. Sorry to bore the ones of you who have already done this, but it's important we go through it anyway. Okay. Any final questions on this stuff before we move on to all the different naming? Okay, let's go. So this page here is high yield. This basically outlines how you name any different molecule, all the different tools that you need to internalize. So you should try to make, I guess, you shouldn't memorize this whole page word for word, but you need to memorize the steps and the different tools that we use along the way. So think of naming organic molecules, and in fact, think of organic molecules as big Lego structures. You can mix and match and you can put pieces together, and that will make different molecules. That depends also, that will then change how you name them. So that the same way that you construct a molecule, when you construct the name of the molecule, it's like attaching pieces of Lego together, and there's a specific instruction manual that you have to follow. This is it. So instead of doing the usual way that most schools do, they go teach you alkane, alkene, alkyne. What I'm going to do is I'm going to show you probably one of the hardest molecules you have to name. Try to follow along with the steps I'm doing. It doesn't matter if you get lost, but try follow the steps. You won't know the names yet, but the important thing is all the different rules. So this here is a skeletal formula. Can everyone count how many carbons are present? And type in chat how many carbons total. Type in the chat how many carbons total in this structure. We got votes for 10, 10, 10, 10. I think it's 10. So it is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're correct. That was just testing. Doesn't really matter in the scheme of naming. The first step we take for naming any molecule is to determine the longest carbon chain. And when we say longest carbon chain, that's how many adjacent carbons we have next to each other. So what's the longest carbon chain here? Ignore the name on top. What actually is the longest chain? How many can you count that are consecutive to each other? Again, be brave, get things wrong. Doesn't matter if you get it wrong. No one cares. 7, 7. Sevens. Okay. It is in fact 7. We have 7 carbons going across the top. However, there's an important rule when we figure out our parent chain, apart from just picking the longest one. We also have to pick the chain that contains the functional group. So if you ever have a functional group on your main chain, if you have a functional group on your organic molecule anyway, you must include it within your parent chain. You must include it within your parent chain. And so the parent chain's length would actually be 6 carbons long in this particular instance. And the reason is you have to include any functional groups. We have a functional group which is a alcohol or hydroxyl here, which is why we must include it. So that's the first step. Secondly, we then determine how we number this chain. We need to assign, oh wait, before we assign the locants, we need to determine what other substituents, side chains, or functional groups we have present. Does anyone know what these are called? These that I'm drawing in purple. What are these called? Branches, correct? They're branches or side chains. You can call them either. And they have specific names as well. So these are called alkyl generally. Alkyl branches, alkyl groups. The one to the left is a methyl, and so the one to the right is a propyl group. And you'll see these prefixes start to creep in. I want to draw your attention to this part here. So meth, eth, prop, but, pent, hex, hept, oct. These describe how many carbons are present in a particular chain. So methane tells us there is one carbon in our carbon chain. Ethane tells us there are two, and so on and so forth. So in the main chain of 6, we would call this a hexane chain or hexane parent chain because there are 6 carbons in it. Methyl describes that we have 1 carbon coming off the main chain, and propyl describes that we have 3 carbons coming off the main chain. Okay, have I lost anyone yet? Any questions? Please ask. If you're feeling lost, I can re-explain things. The third step, we have the lowest locants. We have to assign locants to the main parent chain. When we assign locants, what that means is we number each carbon in the chain going 1, 2, 3, 4, 5, 6, and we either number it from starting from the left or we start it from the right, going 1, 2, 3, 4, 5, 6. The way we decide if we go from left to right or right to left is in order to minimize our functional group's number. So it makes more sense here to number from 1 going to 2, starting from the bottom or the right, in order to make our alcohol group only have a number 2 attached to it. This would have a number 2, as is on the second carbon. It would be wrong to number your chain going the other way, because this would mean the number is not minimized. It would be 5 in that case, and that's wrong. That would be bad. Okay. We've assigned the locants. There's some other steps that aren't relevant to this particular molecule, but if you have more than one of the same functional group or substituent, you have to say that you have more than one present. And we use a separate set of prefixes. We use a separate set of prefixes. So for example, if you had a chain that was like this, how many carbons are in the longest chain here? Hold your fingers up. This is a skeletal formula. How many carbons in the longest chain on this molecule? We've got 3. Any others want to jump in? And we're going to dispute Gibran. Okay, it is 3. We'd have 1, 2, 3. And this has 2 carbons coming off the main chain, each 1 long. So what would you call these? What would you call these branches coming off specifically? You saw them just before. A single carbon coming off the main chain. We can use this
Methyl.
Methyl, perfect. These are methyls. So we have 2 methyls. And that means when we name this molecule, we would have to describe there being 2. We'd call it a dimethyl. And then you describe what comes after. So dimethyl describes that there are 2 methyls. Whenever you have 2 of the same substituent or more, you must use a prefix to describe there being 2 or more. So di meaning 2, tri meaning 3, so on and so forth. Okay. Are there any questions up to here? Anything at all? It can be the stupidest question, I don't care. Okay. Then you must have perfect understanding. 5, if we have all of our pieces now, all of our locants, all that's left to do is just put it all together. So we have all of our Lego pieces assembled. We just need to chuck everything together now in a big name. Side chains and alkyl halides. These come at the front. Alkyl halides are basically just whenever you have a bromine, chlorine, iodine, or fluorine attached to the main chain. These all come at the front. So in our instance, or in our molecule here, we have two alkyl groups. We have a methyl group and we have a propyl group. These would be named at the front of our molecule. So methyl and propyl. And sorry, this should be propyl in the written formula there. They come at the front. And the functional group, the alcohol, always comes at the end. So the suffix for alcohol is OL, comes at the end. We write our locants directly in front of what they describe. So because the alcohol has a 2 as its prefix, it takes a 2 in front. Hi, Tisha. The alcohol takes a 2 in front of it, so 2-ol, and the methyl and propyl are both coming off the third carbon, meaning they take a locant of 3. 3-methyl, 3-propyl, hexane, 2-ol. And that's how we name every organic molecule. These are the steps you follow. That would have been a lot, especially if you haven't seen this before. But this is as bad as it gets. The point of that was just to show you how bad it can be. Everything from here will feel a little bit better. And just some etiquette with how we use commas and hyphens. So for example, if you have 3,3-dimethyl hexane 2-ol, you'll notice that between numbers, so number and number, we put a comma in between. If we have a number next to a word, we use a hyphen. So this is here. And if we have two words attached to each other, so methyl and hexane, we don't have any punctuation between words. So it's just word, word. No space, no comma, no hyphen. Okay. Good. So this whole page, high yield, I would make a mental note to always come back to here. You probably have your own framework as well, but this is important to have. Okay.
Wait, what's the hexane? Or am I just bugging?
Oh, yeah. Good question. So hexane describes that we have 6 carbons in the main chain. So hex describing 6 carbons, and an describes that all of these carbons in the main chain are only bonded to each other with single bonds. We'll talk about that in a second. You shouldn't know that yet, unless you've done it before. So good question. Thank you for that, Benji. Does that make sense? Okay, let's move along. Hydrocarbons is our first venture into naming all of the different Lego pieces. So now you have the instruction manual. You can follow the instruction manual, but without the names of all the little pieces, you're never going to be able to locate them and put them together. So now we're going to learn all the names of the Lego pieces as we assemble our, I don't know, Bionicle or Barbie Playhouse, whatever it is you're doing. So you have alkanes, alkenes, and alkynes. These are the first 3. Hydrocarbons are what we call these 3 organic molecules. And hydrocarbon refers to things composed entirely of carbon and hydrogen. So hydrocarbon, it's only got hydrogen and carbon in it. They can be saturated or unsaturated. We'll talk about them in a second, but let's talk about what each of these are first. An alkane is where you have only single bonds between all the carbons in the chain. So these over here on the left, these are all alkanes because they only have single bonds between all of the carbons. Alkenes are where you have at least one carbon-to-carbon double bond, and these are shown in the middle column. So carbon-to-carbon double bond all through these. And finally, alkynes are where you have a triple bond between carbons. So all of these on the right, triple bond between carbons at some point on the chain. That makes these alkynes. Each of these have their own suffix. So if you have an alkane, the name will end in ane. If it's an alkene, it will end in ene. If it's an alkyne, it will end in ine. And whenever we see alk is referring to some carbon chain. Carbon chain, and we replace alk in any name with the meth, eth, prop, but prefixes. So we'll do a quick quiz. Fingers up, everyone. 10 fingers. Fingers up, 10 fingers. Show me how many carbons there are in a but. But. It's 4. How about eth? Eth. 2. Prop. Balloons. 3. And how about hex? 6 for hex. Okay, so there's all the different prefixes. If you get lost at any point during the session, they're all here. Meth, eth, prop, but, hex. I skipped pent. Pent, hex, hept, oct. Correlating from 1 through 8, telling us how many carbons there are. Okay, let's have a go at naming a few of these. So let's start with this one here. Everyone type in chat what this would be. Ethane, ethane, ethane. It is in fact ethane because this is an alkane. There's only single bonds between carbons. Only single bonds between carbons is an alkane chain. And when there's an alk, we replace the alk with how many carbons there are. Ethane. How about this one over here? Once again, type in chat. Propene, prop, 1-ene. We've got a propane. Okay, so we've got a bit of dispute between. It is definitely an alkene, so it wouldn't be propane. But in terms of whether it's prop 1-ene or propene, does anyone have an opinion on this? Of those who have already done a little bit. Prop 1-ene versus propene.
Well, isn't it technically correct to say both, but like prop 1-ene is like more specific? Is that it?
Yeah, so prop 1-ene would be more specific. But in this particular case, because imagine if you had this molecule the other way around. So instead of doing this way, so this would be prop 1-ene. Is it possible to have prop 2-ene? That's the question. Is it possible to have prop 2-ene? Or is that just the same molecule?
It's the same.
It's just the same. So there's no need to actually say prop 1-ene. You could just say propene here because prop 1-ene would be the only configuration of this. So whenever you have only one configuration possible of a molecule, you don't need to specify locants. So propene would be the best answer here, but this is also not wrong. Prop 1-ene. Have a go at the next one along. How about this one? We've got some condensed formula. What's this? Type in chat. Love it. Okay. So it's 1, 2, 3, 4, 5, 6 carbons. It'd definitely be hex. And the question is, do we need a locant here? Do we need a locant here? We do. We need a locant here. because we could possibly have this double bond between the first and the second. We could have it between the second and the third. We could have it between the third and the fourth. These would all be different configurations of hexene. So we have to specify which hexene we actually have. So this is hex 3. Oh, I forgot which one it is. Hang on. Let me clear all this. Hex 2-ene, sorry. Hex 2-ene. Because it lies between the second and third, so the lowest possible numbering is for the second. We call this hex 2-ene. Any questions on that?
How do you, where like the numbers come in? Because I don't really understand that.
Yeah, great question. So the numbers come in whenever you have a long parent or any carbon chain, right? You need to assign numbers to each carbon in order to figure out what the locants are for each part. So the way that you can number a chain, you always start from one end and number all the way along to the other end. And you could do it one of these two ways, right? You can either go from left to right or right to left. But one of these is better. We always want to make sure our functional group's locants are as low as possible. So the reason why the top numbering is better is because that would mean our alkene group gets the locant 2 instead of locant of 5, which is a lower number. We always want to minimize our locants. So the way we'd number this one would be using the top line of numbers. Does that make sense, Isabel?
Yes, but where did the 2 come from?
What do you mean?
Like when you say hex 2-ene.
Oh, right. Okay. So the ene group is this double bond between carbons. And when we say hex 2-ene, we're saying that the alkene is located on the second carbon. So it's
okay.
hex 2-ene because it's on the second carbon.
Okay, thank you.
Great. Good question. Cool. And let's do one more for the alkynes. Have a go at this one here. And to be clear, whenever you see a triple bond on skeletal, each end of the triple bond represents a carbon. So just keep that in mind for this one. How would you name this? Type it in the chat. It always takes one and then everyone follows. Okay, great. So it is in fact pent-2-ine. Very well done. 1, 2, 3, 4, 5 carbons, pent, and we number from the left to right to minimize the number of our functional group. This becomes pent-2-ine. Very well done. Okay, let's move on. I think we've got the basics. Hydrocarbons done. Tick it off your syllabus dot point. Let's move on to the methyl and ethyl groups, or what we generally call alkyl groups. So these alkyl groups are also what we referred to as side chains before. Side chains or branches. Side chains or branches. And again, they're alkyl. So what do you think would be the names of these? It would be replacing the alk with meth, eth, prop, but, so on and so forth. So you can have methyl, ethyl, propyl, right? And each of these refers to how many carbons comes off of the main chain. So if you had a methyl group, as shown here, coming off the main chain, this would be referring to any of these, to be honest. You could say this is the methyl coming off the main chain of 3. There's a main chain of 3 carbons, and coming off of that, there's a single carbon. Side chain, alkyl group, methyl group. Specifically, it's a methyl group. So this here is our side chain. Things that are really important to note with side chains, you should be always be wary that the side chain you actually indicate is if it's a long side chain, it might not actually be a side chain. It might be contributing to the parent chain. So for example, if I extended this side chain to what would seem like an ethyl group coming off of the previous main chain, does everyone see how this might affect the main chain? The main chain before was only 3 carbons long, and that dictated that that would stay the parent chain. The problem here is now there is a longer chain possible. This has now become a butane chain with a methyl coming off. So just always be wary when you're naming side chains, check if it's part of the main chain, especially if you have longer side chains. Okay. Oh, and also, adding on to that, you can never have side chains coming off as one methyl. So if you tried to add a methyl group on here, again, what have you just created? What chain? Someone shout it out. Is this a methyl group that I've just drawn on?
Becomes a butane, right?
Becomes a butane. Perfect. So this now extends into a butane chain because it can go of 4. So just be very careful. Okay, let's have a go at naming some of these. I'll take you through the first one. So this here, what's the longest chain? Fingers up. Longest chain. 4. So we must call this a butane. Butane will be describing this length of chain here. So we've still got this methyl coming off it. Do we put methyl groups at the front or the end of a name? Front or the end?
And
Do we have any seconders for end? Or anyone in dispute?
Isn't it the front?
At the front? It is in fact at the front. We put methyls at the front. Methyls at the front. So alkyl always comes at the front. And the other group that comes in the front we'll talk about in a second are our haloalkanes. So there's only 2 things that tend to come at the front. Haloalkanes and meth and alkyls. In this case, we have a single carbon coming off. So this must be a methyl. And we refer to this as methyl butane. Is this enough just to say methyl butane?
You've got to put the 2, don't you?
I mean, we could put the 2, but is it possible to have one methyl butane? Is that possible? What would one methyl butane actually be called? Lucy, I see you shaking your head. What would it be called?
Like hexane. Oh,
Not
sorry,
quite.
pentane.
Yes, pentane. Perfect. So if you just added on a methyl onto the end of this chain, that would actually just extend the chain. That's what I was saying before. This would become a pentane. So be very careful. So it actually would just be enough in this case to leave it as methyl butane if you wanted to. But always, if you're not sure, just leave the locant in. If you're not sure, just leave the locant. Okay, so this is 2-methylbutane or methylbutane. Have a go at, let's do this one. Actually, that one, and no, let's do this one underneath. Okay, these 2, type in chat when you have your answer. When you finish the first one, move to the second. Sensing some confusion on the second one. Okay, we've had some brave souls going in for the second. So the first one we'll go through quickly. So it is a pentane, 1, 2, 3, 4, 5. And we have a methyl coming off of the third carbon. So this one would be a 3-methyl pentane. And numbering across, we can do it either way here, it'll be symmetrical. Comes off the third carbon. And this second one, we have 1, 2, 3. I guess you can do it 4 going down, or you can do it 4 doing up. Doesn't really matter. We have the longest carbon chain of 4. Doesn't matter which way we number again. This is also a symmetrical molecule. So that means that we have 2 methyl groups coming off of the main chain. So it is a dimethyl. And because they come off the second and third carbons, this is what we call a 2,3 dimethyl. 2,3 dimethyl butane, where butane describes the chain and the 2,3 dimethyl describes those 2 methyls coming off of the second and third carbon. And one other important thing, which Lucy and Gibran have done very well, whenever you have multiple methyl or multiple of the same substituent or functional group, you must show you have multiple using a prefix. So di shows you have 2 methyls, and you have to show where each of those is located using their own locant. So if you have a prefix of di, you would need 2 locants in front. If you had a tri, you would need 3 different locants in front to show where each of those are. Okay.
Could you just explain how you got the 2,3 again? The 2,3.
The 2,3, yep. So the carbon chain is numbered 1, 2, 3, 4 along the chain, and each of the methyls comes off of carbon 2 and carbon 3. So you'd have to say 2, 3 hyphen to show that the methyls come off carbons 2 and 3. Great question. Moving along. Have a go at this one here. And by the way, from here, I'm just going to start picking up harder ones to throw you off on purpose. I'm not going to pick easy ones. The point is to make mistakes. So have a go at this one. First question you should ask yourself, what is the longest carbon chain? And then go from there. Okay. Cool. Great. So we have some answers here, which aren't agreeing. Let's talk through them. First question, longest carbon chain. And you should have gotten that there were 1, 2, 3, 4, 5 carbons in the longest continuous chain of carbons. So we have pent something. We have a double bond. This makes it a pentene. And the question is, first of all, do we need to specify where this pentene is on the chain? Are there more than one configuration for where the pentene could be? Can be. It could be on the second, between the second and the third. It could be between the first and the second. And then the other 2 options would just be mirror images of those first 2. So we do need to specify where our pentene is. And we can number it from left to right to minimize the functional group. When I say minimize the functional group, alkenes are functional groups. Alkyl groups are not functional groups, so we don't care about those in priority. Pent-2-ene is what we find here. Pent-2-ene. And then we have to worry about this methyl. If we number the rest of our chain, 1, 2, 3, 4, 5, that methyl comes off the 4th carbon. This has to be 4-methyl. Sorry, that's hard to read. 4-methyl pentane. Pent-2-ene, rather. Does that make sense for everyone? Thumbs up, thumbs down. On a scale of 1 to 5, 0 being completely lost, 5 being following, where are we? 1 to 5. Be honest, it's fine. 4, 3, 3, 4, 3. Okay, that's fine. 4s and 3s is okay for me. If it drops to a 2, let me know. Okay, we're going to move on from alkyl. So we've done hydrocarbons, we've done alkyl side chains. And the same thing can happen if you do these alkyls off of an alkyne. Same rules apply as the alkenes. Halogenated organic compounds, also known as alkyl halides or haloalkanes. So halogens, there are 4 of them: bromine, chlorine, fluorine, iodine. If you see these coming off of the main chain, this is now a alkyl halide or haloalkane. Now, the prefix that we use is each of these halogens. So for example, bromine. Bromine, you snap off the ene and you replace it with an O. Bromo. So bromo, chloro, iodo, or fluoro are the prefixes that you'll be using. And these all come at the front of the name with the alkyl groups as well. Okay. So let's start with an easy one. Have a go at this one here. Typing in chat what you think the answer is. Iodomethane. Great. Iodomethane. Why do we need a locant in front of the iodo? Why no locant? Sydney? So there's only 1 carbon, so there's no point putting a 1 in front of iodo. There's only 1 carbon. Okay, let's move on. Have a go at this one here, and then have a go at this one here. Okay. So once again, we have a mix of answers. Is the question, do we need to say 1,2-dichloro or can we just say dichloro? And the answer basically lies in the molecule above. Can you see how the above molecule is also a dichloroethane? So we need to be specific here. Are we talking about 1,1-dichloro? So this one above will be 1,1, and the one below will be 1,2-dichloro. You do have to specify locants here. So if in doubt, always just specify your locants. 1,2-dichloroethane. 1,2-dichloroethane. Have we got the last one?
Wait, where does the 1, 2 come from?
Yep, good question. So each of these carbons would be assigned a number. So you could do it either way because it's symmetrical. So say you do 1, 2. We're saying that there's one chlorine on each carbon. So one chlorine 1 and chlorine on 2. So 1,2-dichlorine. Good question. Last one. Think about which one comes first. I didn't mention this. The rule is that you alphabetically order prefixes. All right. The second one, bromo comes before chloro because it's alphabetically first. However, whenever you have things that are the same priority, so bromo and chloro are the same naming priority, you just number whatever comes first as the lower number, whatever comes first. So you would actually go 1 bromo, 2 chloro, propane. And some of these things, it's totally fine to have gotten it wrong because there's no way you could have known unless you've done the question and gotten it wrong. But now you know, so it's fine. 1 bromo, 2 chloropropane. And I just want you to have a look at this molecule up here and have a look at the name. 1,1-dibromo, 2,2,3,3 tetrachloro, 1,3-difluoropropane. And just have a look at each of the atoms and fact check that name is correct. So just have a look at yourself. Look at where the bromines are. 1,1 bromine. So this must be carbon 1. We have 2,2,3,3 tetrachloro. 2, 2, so there's 2 on 2 and 3 chloro and 1,3-difluoropropane. So yes, it does make sense, but this is as bad as it'll get. You'll never get anything like this in your exam. Just showing you an example of exactly how these all fit together in a more complex name. Okay, any questions on haloalkanes? Cool. Alcohols, moving on. So alcohols are represented by this OH group. And you might see this notation moving forward where you have things attached to an R. So what R means is just a carbon chain of any length. It's general formula, carbon chain generally, if you see an R. And this OH group, this is what we call a hydroxyl group. Hydroxyl. The suffix is OL. So alcohol, you might have heard of methanol, you might have heard of ethanol, octanol, these kinds of things. These are alcohols. Okay. The way we name is we follow this scaffold. Alk and locant ol. Alk and ol. So you might have alkan 1 ol. Where alk we represent with our eth, meth, bute, all of those prefixes. An tells us, do we have C to C single bonds the whole way, or do we have double bonds or triple bonds? And lastly, the ol tells us we have an OH somewhere. There are also 3 types of alcohols to just visually identify for now. You'll learn more about these later, but I just want to show you what they look like. You can have primary alcohols, and listen carefully. Primary alcohols are where the hydroxyl is attached to a carbon which only has 1 carbon attached to it. A secondary alcohol has a hydroxyl attached to a carbon that has 2 carbons attached to it. So 2 carbons attached to it. And a tertiary alcohol has a hydroxyl attached to a carbon, which has 3 carbons attached to it. And that's how you tell primary, secondary, tertiary. Okay. So just to have a quick revision of that primary, secondary, tertiary, is this first alcohol here primary, secondary, or tertiary? Fingers up. 1, 2, or 3? Tertiary, because it has the carbon that is attached to that alcohol has 1, 2, 3 carbons attached to it. How about this one here? Primary, secondary, tertiary. Secondary. The carbon attached to the alcohol has 1, 2 directly attached to it. Only the adjacent ones matter. Only the adjacent one matter. And finally, primary, secondary, tertiary. Primary. The carbon attached to the alcohol only has 1 carbon attached to it. So this is a primary alcohol. Okay, let's have a go at naming some of these. Let's start with an easier one. So we have this here. What would we name this, first of all? Answers in the chat. If you're not sure, use the notes above, follow the scaffold. Okay, we have pent, and we need to show that we have a alkane chain. So we'd also need to show pent and ol to show this is all single bonds between carbons. Pentan, 3 ol. And then let's have a go at some of these other ones, a bit harder. Let's do this one here that I've circled. So longest carbon chain, we always do that first. 1, 2, 3, and we can do up or down, 4. So we have a butane because it's a single to single carbon to carbon bonds the whole way. Butane, we want to make the numbering of the functional group as low as possible. So it would make more sense to number from left to right. 1, 2, 3, 4. Butane 2-ol gives us the number of the alcohol, and lastly the methyl comes off of carbon 3. So that slots on here as 3-methyl butane 2-ol. Any questions on that one? I think that was a bit trickier. Darren and Benji, all good? Isabel, Gibran, any questions? And Sydney and Lucy, any questions? Okay. One more. That's okay. I think we have alcohols okay. Actually, no, let's just do the last one. Let's do this one. Actually, no, not this one. Do the one above. This one here. This one's out to trick you. So have a good think about it. Okay, solid. The trick was that the longest carbon chain you need to have a good think about. It would be 5 carbons. You could do it numbering this way. So this could be your longest carbon chain, or you could have done it including the top part, but there was a 5 carbon chain, and then you had an ethyl group coming off it. So the answer for this, numbering 1, 2, 3, 4, 5, would have been 3-methyl pentan 3-ol. Sorry, 3-ethyl. Apologies. 3-ethyl pentan 3-ol. Good. Any questions on alcohols? Let's keep moving. Accumulating more and more pieces. So up next, aldehydes and ketones. These actually talk about the same group. So whenever you have a carbon bonded, double bonded to an oxygen on a organic compound, this is what we call a carbonyl group. Carbonyl. And depending on where on the chain it occurs, it has a different name and different functional group. So when it's on the end of a chain, so for example, like this is an aldehyde. And we call this and I shouldn't miss these hydrogens while I show you guys for the first time. Normally you have to fill in all the hydrogens. This is a aldehyde when the carbonyl group is located on the end of a chain, when it's terminal. that is an aldehyde. The difference between an aldehyde and a ketone is that for a ketone, the oxygen occurs in the middle of the chain. The double bond oxygen occurs in the middle of the chain. And this would then be a ketone instead. Does that make sense for everyone? Aldehyde versus ketone. Aldehyde is where the oxygen is on the end of the chain, a terminal group, and ketone is where it's in the middle of the chain, a non-terminal group. But it's the same group. It's the C double bond to O. For aldehydes, the suffix is al. So for example, if we had a chain of 3 and an O coming off the end, this would be propanel. And for ketones, if we had this ketone up here where it's a chain of 3, this one would be propan to one. Again, we have to make sure we show our an to show it's a single carbon to carbon bonds the whole way. And the locant is 2 here. Do we need this locant? Is this a necessary locant? Thumbs up, thumbs down. What would happen if we moved to propan 1-one? Is that possible? Propan 1-one.
Wouldn't the suffix be different because there's only 3, so it wouldn't matter in this case?
Correct. So if you tried to do propan 1-one, what you've actually just created is propanal. So here in this instance, propan 2-one, 2 is redundant. You can just say propanone. But in other instances for ketones, you would need to say the locant. So I've just included it here to be clear. Okay. So the suffix for aldehydes is al. Suffix for ketones is -one. Following alkanal and alkanone. Let's have a go at some of these. Which is the left aldehydes or ketones? Left is aldehyde or ketones?
Left is aldehyde.
Left is aldehydes, and the right, therefore, would be ketones, because all of these actually occur in the middle of the chain somewhere. Okay. What would this one be called? Type in the chat. Okay. So we have a carbon chain of 1, 2, 3, 4, has to be bute, and this is an aldehyde group. So the suffix is al. Butanal. And the same thing will be true for all of these. Let's do a more complicated one. How about this one here? Or this be? All right. Once again, longest chain, 1, 2, 3, 4. Question is, do we number from the right to the left or the left to the right? And we always want to minimize the number of the functional group. The functional group here is the aldehyde. So we should number the aldehyde as 1 and following across 2, 3, 4. Now, a lot of the answers that are in the chat have left out the locant for aldehyde. Does anyone want to explain why we don't need a locant for aldehyde? Gibran or Sydney?
Is it because the aldehyde can only exist on the first, like it would always be the first one?
Exactly right. So for aldehydes, they're terminal. They must be on the first carbon, and it's always going to be number 1. It will never be number 4 or a higher number. Aldehyde always has to be 1. And this means our name would be 2,2-dimethyl. The 2,2-dimethyl talking about the 2 methyls coming off the second carbon, and butanol representing the rest of the chain. Good. Ketones. Have a go at this one here. And again, I am picking out slightly harder ones, so it's okay if you don't exactly know, but these are the ones that will help you learn fastest. Okay, good. So pent 10 for the main chain. Question is, do we number from left to right or right to left? And we go from left to right because we have to minimize the number of the functional group. So this would be 4-methyl to represent the methyl group coming off the 4th carbon. Pentan 2-one for the ketone coming off the 2nd carbon. 4-methyl pentan 2-one. Good. Let's move along. Up next, we have carboxylic acids. So carboxylic acids, you would have actually heard of one before in module 6. You would have heard of ethanoic acid very much, acetic acid, and now it actually makes sense why ethanoic acid is CH3COOH. What type of formula is this from the ones we've seen before? Expanded, skeletal, condensed. It is condensed formula. So every time you've seen CH3COH, we've actually been talking about an organic molecule. You've already learned a bit of module 7 in module 6, just didn't really know it. And that molecule looks like this. This is, in fact, ethanoic acid. So ethane representing 2 carbons, and oic acid is representing the carboxylic acid group or carboxyl group. So this is carboxyl, which is a combination of one of these groups. What's this group called? Carbonyl or carbonyl. And one of these groups. What's this OH?
Hydroxyl.
Hydroxyl, perfect. So carboxyl is simply the combination of the ones we just learned before. Carbonyl and hydroxyl combined on the same carbon. And this is also a terminal group. carboxylic acid has to be on the end of a chain. The reason being is once you have a double bonded O and an OH, this carbon only has one remaining electron left on it. So it can't make any more bonds than a single bond to another carbon or to a hydrogen to finish it off. So that's why it must be terminal. No matter what, carboxylic acid has to be terminal. Always terminal. And if it's always terminal, does it need a locant? Thumbs up, thumbs down. Does not need a locant. Definitely doesn't. So the suffix oic acid, you add it on after the alcan, describing how many carbons and the nature of the chain, single, double, triple bonds present or not. Hopefully it's starting to become a bit repetitive now. It's the same thing over and over. You just have different puzzle pieces you're putting on. So try this one. What's this? Type in chat. First one there. That's it. Butanoic acid. Oh. Butanoic acid. Perfect. And have a go at one of these. What about this one? What is this? Good. Okay. So it is 2-ethyl hexanoic acid. And just to make sure we know where the locant comes from, hexanoic acid is the functional group here. It is a very high priority functional group. In fact, it's the highest of them all. So this must be numbered as 1 to keep it low. 2, 3, 4, 5, 6. Therefore, the ethyl group, which is 2 carbons, comes off of the second carbon. That's how we named that. Any questions on carboxylic acids? Okay, keep going on. And we arrive at the hardest 2 functional groups to name, amines and amides. Amines and just below amides. Now, there's 3 types of amines and 3 types of amides, but you can group them as primary and then secondary and tertiary, you sort of name in the same way. Primary amines are really easy. So amines, first of all, these are NH2. So any NH2 that comes off the main chain is what we call an amine. And these, when it's in the NH2 form, this is a primary amine. Primary amine. So primary amines are very easy to name. If you have a chain of 5 carbons all attached to each other, and you have, for example, an amine coming off the second carbon, like so, this is what we call penten 2 amine. So the suffix is simply amine. Where it gets messy is once we get into secondary and tertiary amines. So secondary and tertiary amines, if you have a look at these, does someone want to have a go at describing what they can see in terms of what makes an amine secondary or tertiary? What does it look like?
So how many carbon chains it's got attached to it?
Attached to what specifically though?
The nitrogen.
Attached to the nitrogen, correct. So the primary amine has only one carbon attached to its nitrogen. Secondary amine has two. Tertiary amine has three carbons attached to the nitrogen. To the point where a tertiary amine doesn't even have hydrogen attached to it anymore, which is why it's so confusing sometimes to still call it an amine. But it is an amine. Okay. How do you name these then? That's the question. And the best way to do this is I'll just demonstrate with this particular name. N-ethyl propan 2-amine. What does this mean? We'll start with a propan. Propan is 3 carbons, all single bonded to each other. 2-amine. There is a nitrogen coming off of the second carbon on the chain. N-ethyl. N-ethyl means that there is an ethyl group coming off of the nitrogen. So this is referring to nitrogen when you see an N as a prefix. There is an ethyl group coming off of the nitrogen. And that is our N-ethyl propan 2-amine. Just be wary that there's a new locant that is actually a letter N. When something comes off an N, it is coming off a nitrogen in an amine group. Okay. And adding on to this, we could have another ethyl group. It's kind of guy with his hands up like this now. So if we have 2 ethyl groups and both the ethyls are coming off of the N, is this now, do we agree this is now a tertiary amine? There's 3 carbons attached to the nitrogen. 1, 2, 3. This is now tertiary. And this would now be N diethyl 2-amine. Sorry, I've missed a whole part of the name. Diethyl propan 2-amine. The NN diethyl is talking about these 2 branches up the top, or these 2 chains, and the propan 2-amine is talking about all of the remainder of this. And that's how we cover all bases in this name. Yes, Gibran.
Just with like the naming, because between like numbers and letters is a hyphen. So do you just like consider N as a number for this case?
That's correct. Good question. You consider N as a locant, so a number in this case. And you'd separate the N's by commas. And to add on to that, N's come before numbers. So if you had an N and a 2, you would show N2 dimethyl, for example. Does that make sense?
Yep.
Good question. Okay, that's secondary. We've also touched on tertiary. Let's have a go at naming some. Actually, before we name any, because we haven't done any drawing yet, I'm going to throw you guys into the deep end. I'm going to give you 1 minute to try draw this structure. Can you draw it in expanded form? So show every atom, show every bond. N-ethyl, N2 dimethyl, propan 1-amine. If you get it completely wrong, that is so fine, but just have a go at it. Try to figure out what each of these things mean and place it together in a structure. I would start from propan. Okay. So, in scale of 1 to 5, how did drawing that molecule feel? 5 being super easy, 1 being what on earth's going on? 1, 2, 2, 2, 1. Yeah, that's totally fine. It's the first time you drawn a molecule and it gave you basically the hardest one you're ever going to draw. So now I'm going to try to piece together how exactly we drew this molecule. In purple, first of all, is the propan chain. Hang on. Propan. Sorry, my methyl is now in the wrong place because I moved a carbon across. Let me just fix that quickly. Okay. So the propane chain is shown in purple. That's the first component here. Propan. The next thing that I worked on, I went and did my 1-amine, which is the nitrogen attached to the first carbon on the chain. So this is talking about this amine here. This is 1-amine. From there, I went and worked back to the prefixes. N-ethyl, N2-dimethyl. That tells me there's an ethyl on the nitrogen and 1 methyl on the nitrogen too. So I've gone in and drawn the ethyl over here. So this is an N-ethyl and this is an N-methyl. And finally, there's this 2-methyl as well on the N2-dimethyl, which means I draw in a methyl on the second carbon on the chain. So numbering chain across, 1, 2, 3, that slots on the second carbon to make a 2-methyl. Again, this is the hardest drawing you'll probably do in the whole of your chemistry learning. Does that make a bit more sense after having explained it? Is anyone still confused about any of the drawing? Yep, Javon?
Will we ever get like any branches on the like carbons attached to the like nitrogen? Will there
I
ever be
would
like
say very unlikely. Very unlikely. You can get branches off of your main chain, but I wouldn't say you'd have branches off of branches on nitrogens. That would be unfair of them.
Yeah.
Okay. All right. So let's have a go at naming a few of these. Now we've drawn one, the worst of it. So these are first of all, is this primary, secondary, or tertiary amine? Fingers up, primary, secondary, tertiary. Primary, because there's only 1 carbon attached to the nitrogen. Is this one here, primary, secondary, tertiary? 1, 2, 3. Primary, secondary, tertiary. Tertiary, because there's 3 carbons attached to the carbon attached to the nitrogen. And finally, this one, oh, that's just primary again. Finally, where is the secondary one? Hang on. Sorry, that was primary again. I got gaslit. That's primary again. Because this would be from the system of an alcohol, a tertiary alcohol. But amines, we're worried about how many nitrogens are attached to, sorry, how many carbons are attached to the nitrogen. This would be tertiary. So a tertiary amine would be, for example, this. This is a tertiary amine because there's 1, 2, 3 carbons attached to the nitrogen. So a secondary amine would therefore look something like this, where there's only 2 carbons attached to the nitrogen. Does that make sense for everyone? Okay. Have we got naming this amine first of all? This one should be straightforward. What's this? Pentan 3 amine. Good. Pentan 3 amine. And then let's have a go at naming this one here. What's this? So if you're unsure, start from the longest carbon chain and then figure out what the methyl or ethyl groups are. Okay, nice. So it is N, well, I mean, let's start how we work it out. Longest carbon chain is 2. So that means this will be the parent chain for this amine. If it's 2, it will be an ethane, amine. And we actually don't need a locant here because there's only one possible configuration for the amine. It could be on the first carbon only. So ethanamine is fine. And then we just show that there's this methyl group coming off of the other side. So it would be N-methyl ethanamine. And that's all we need. Let's do one more. Have a go lastly at this one here. Okay. Hands up if we need a bit more time. Or hands up if we're now lost. Okay. So the tertiary amine becomes the hardest one to name because now there's 3 branches coming off of the central nitrogen. We've got the first task always is to figure out which is the longest carbon chain. So our longest carbon chain is here, or it could be here. It's 2 carbons long. So that's our first step. Ethane. It's an amide. The amide is coming off the first carbon. It doesn't really matter which way you arrange it. It's always going to be the first. So we're just going to take this right one as our longest chain. It's the same thing. You could do it either way. So this is ethanamide. Sorry, amine. Have I been writing amide? Good. Okay, amine. Then we have two things coming off of the nitrogen. So what is this, primary, secondary, or tertiary amine? Primary, secondary, or tertiary? Tertiary. Tertiary amine, because there are 3 carbons attached to the nitrogen. So we have a methyl coming off. The methyl is at the top, and we have an ethyl coming off the bottom. Therefore, this is a N-ethyl, N-methyl ethanamine, signifying that we have an ethyl coming off the N as well as a methyl coming off the N, and that N or amine is attached to an ethane chain. Pretty big mouthful. Are there any questions on this one after having explained it? Okay, there'll be a few more like this as we go through amides as well. So amides actually follow the same naming conventions as amines because they also have a C and an NH2, except the main difference is that there is a carbonyl. So there's a carbonyl group and there's an amino group for the amine. So this is amino and carbonyl. Together makes an amide. Okay. So amides can be primary, secondary, or tertiary as well. And the naming convention follows quite similarly. For this first one, what do you reckon? This is the primary, secondary, or tertiary amide? Primary, the nitrogen's only attached to 1 carbon. So this must be called what? Type in the chat. This one's okay. The suffix for amide, by the way, is amide. This is methanamide. And moving on to a harder one, the naming is quite similar when we move on to the secondary and tertiary. Actually, yeah, this one would be, let's just do this one. So the naming for this one, just to take you through it, the longest chain is 4, 1, 2, 3, 4. So it's a butane chain. We can see it's an amide because there is a double bonded oxygen and a nitrogen on the same carbon. So we can say this is butane amide. And you'll notice that I've left out the locant because amides are also always terminal. Always terminal. For the same reasons as carboxylic acid. Finally, there's 2 methyl groups attached to the front or attached to this nitrogen. So the suitable prefix would be N-dimethyl butanamide to signify that there are 2 methyls coming off the nitrogen. It's okay if the amides and amines aren't making sense. They are the hardest. They'll take some time. Okay. In the interest of time, we're just on 2. We're going to go a little bit over time today. So if you have to head off, by all means, we'll finish up probably in about 5-10 minutes. Probably 10 minutes, I'd say. Esters, I won't go over the questions, but just to introduce them. The ester group looks like this. Actually, I'll draw it the other way. More intuitive. It looks like this, where you have a single bonded oxygen attached to a carbon and a double bonded oxygen to that same carbon. So this is an ester. Once again, this is a carbonyl group. And this single bonded oxygen is actually what we call an ether. Don't need to know what that is. That's outside of scope for HSC. The way we name it, the carbon chain that comes off of the side with the oxygen, this is called an alkyl group. And the carbon chain that comes off from where the double bond oxygen is, including the carbon that's in there, is an alkanoate. So esters names are alkyl, alkanoate. So if we have this ester down here, this side, does it take the alkyl or alkanoate form? Hands up for alkanoate. Hands up for alkyl. It takes the alkyl form because it's attached to a single O. The other side here would take the alkanoate. And the easy way to remember it, alkanoate is on the side with the O. Alkanoate is on the side with the O. So the name of this would be ethyl methanoate. Ethyl methanoate. And these have their own kind of unique naming system. It's not too complicated though. So you won't see this again for a while, just to show you these exist. Okay. That is all of the naming that you need to do in module 7. So everything that you see now, you should be able to name, in theory. In theory, of course. It's going to take some time, but you have the tools available to you. These aren't syllabus. I thought I'd just show you anyway. This is what a benzene looks like. It's this ring up here is what a benzene is. And one other thing that you'll see are these circular structures. Sometimes you might see these. These are what we call cycloalkanes, where it's essentially just a ring of carbons. So this particular one I've drawn is 6. You could have 2. This would be cyclobutane. These come up as well. So this would be cyclobutane, or skeletally it'd just be a square. You can also see these cycloalkanes, alkenes, alkynes come up, but much more rarely. Okay, very last thing I want to talk about today, isomers. Has anyone heard of these before? Hands up, you heard? Okay, great. So isomers, basically all they are molecules that have the same molecular formula. So for pentane, the molecular formula is C5H12. Molecules that have the same molecular formula, but are arranged in a different way. So for pentane, this is an isomer of 2-methylbutane. They'd have the same number of carbons, 5, and they'd have the same number of hydrogens, 12. But they're just different arrangements of the same number of atoms. There are then 3 subsets of isomers: chain isomers, position isomers, and functional group isomers. You need to know what each of these 3 are. So what we just saw with pentane and methylbutane, this is what we call a chain isomer. Chain isomers are where you have the same molecular formula, but the shape of the carbon chain is different. It's either longer or shorter. So in pentane and methylbutane, we change from a carbon chain of 5 to a carbon chain of 4 by moving one of the carbons along the chain to elsewhere. Similarly for butane and 2-methylpropane, this is a carbon chain of 4, this is a carbon chain of 3. These are chain isomers. Any questions on that? Okay. So if we were to try to figure out how many chain isomers there are for C6H14, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. How many different ways can you arrange the chain for C6H14? That's the question. Everyone have a go quickly. Try get 1 or 2 out. If you can get more, by all means, try get 1 or 2 at least. How many different ways can you arrange the chain so to not change the molecular formula? Okay, if you got 1 or 2 out, that'd be good. But I'll just show you what I mean by we don't change the molecular formula when we change the chain. So if we were to move one of these CH3 somewhere else on the chain, let's say we moved it into this spot here, and we chucked on a CH3 and moved it across, what would replace that CH3 is the the hydrogen that we just replaced. So whenever you move a carbon to elsewhere on a chain, the molecular formula doesn't change. You're simply moving around a hydrogen and swapping it with a CH3. And so the different arrangements you can do would be to have a chain of 5, move it along again. And if you have a chain of 4, you can have these 2 arrangements as well. These would all be different arrangements of this as isomers. Okay. Finally, position isomers and functional group isomers. Final thing. We have chloropentane and 2 chloropentane, 3 chloropentane. A position isomer is where you have the same functional group or substituent and you just move it along the chain. Move it along the chain to a different position. So 2 chloropentane has been moved onto the 3rd spot in 3 chloropentane. In 1 chloropentane, same another isomer, you would have the chlorine on the 1st spot. And these are all position isomers. The functional group is the same, but you're just moving them along the chain to elsewhere. And finally, functional group isomers, these are the weirdest. If your functional group changes when you change the structure, for example, you move a carbonyl group on a ketone to the end of the chain, you would make an aldehyde. So you've changed the functional group. This is a functional group isomer. The other example that commonly comes up is carboxylic acids and esters commonly have functional group isomers between them as well. So as the very last exercise, for this molecule, can everyone draw 1 chain, 1 position, and 1 functional group, and we'll call it a day on inquiry question 1. Draw 1 chain, draw 1 position, and draw 1 functional group isomer. All right. So the chain isomer you could have drawn is you could have moved one of the carbons to elsewhere on the chain. This would have made a chain isomer with a shorter chain length of just 5. Position isomer, you could have moved the carbonyl group to, the 2 options that look appealing are you could put it on this 4th or you could put it on this 2nd. Which of these would make an isomer, the 2nd or the 4th carbon? The 2nd carbon. This one would only be the only one that actually makes an isomer, because if you move on to the 4th, that'd just be the same as the 3rd. It'll be a mirror image. And finally, functional group isomer, we can just move along that carbonyl group right to the end of the chain, making us a hexanal. We'll change from a ketone to an aldehyde. And that's the end of inquiry question 1. There's more questions in here and more naming that you can practice, but I can't cover it all in a session. So if you need more practice, there's plenty for you to go back over. So you've got holidays. I'd recommend that this is a good start. Try name a few more molecules. But the other thing that I would highly, highly, highly recommend you make use of is the homework on the Google Classroom. So you should have been able to access that. And if you haven't, just send me a message to sort it out. The homework is up there under week 1. You can download it, have a go at it. It's about 30, 40 marks each week. And it's basically the best thing you can do to get consistent practice. You get it marked back for you by the next session if you get it in before 5 days from now. So today's Sunday. If you submit it by Friday evening, you'll get it back by Sunday morning. And that's basically it. If you have any questions between class, put them on the Google Classroom and we'll get around to them as soon as we can. But otherwise, that's all of inquiry question 1. You've learned literally everything in terms of the naming. You've learned every molecule. So take a deep breath out. You've expanded your world sideways. Now all that's left is to build some buildings on it out of the Lego that you have. That's all it is. Enjoy the rest of your break. Your weekend, and then your break until next week. And I'll see you all then.
Thank you.
No worries.
Thanks, bye.
No
Thank
worries.
you.
All good.
Sorry, sir. I just had a question.
That's all good. Don't call me Jeff. Don't call me sir. I'm not that old yet.
Would we be able to access like the module 5, 6,